Okay, intermolecular forces. These are forces that are between molecules. So we talked about ionic and covalent bonds. Okay, ionic versus covalent. These are what's called intramolecular forces, meaning within a molecule. So like if we have water, this is a covalent bond. Those are the bonds I'm talking about. Sodium chloride, all right, this interaction between this positive and negative is what's called ionic bond. These are interactions between the molecule. Intermolecular forces, in the molecule, are forces between molecules. So imagine I have a water molecule and I have another water molecule. Okay, well, these two water molecules, sorry about that. These two water molecules are attracted towards each other. So this water molecule and this water molecule are attracted towards each other. Okay, this force right here is called an intermolecular force. It's the attractive force between two molecules. Remember, the attractive force between two atoms is called a covalent or ionic bond. This is between atoms. Okay, I think I said molecules by accident earlier. I meant to say atoms. Forces between atoms is called the intramolecular force, ionic covalent bonds. But between molecules, this molecule and this molecule is called an intermolecular force. And there are three forces we're going to talk about. One is called the London dispersion force. Okay, this has also been called a van der Waal. Some of you might have heard it as a van der Waal force, basically the same thing. Dipole-dipole interactions, and then hydrogen bonding. This is in order of increasing strength, how they show you. Okay, this is the strongest. Hydrogen bonding is the strongest, and the London dispersion is the weakest. Okay, the strength of the intermolecular force determines how high or low the melting point or the boiling point, and if it's going to be a solid, liquid, or a gas, or temperature. So just by looking at the molecule, and by determining the intermolecular force, you can kind of gauge some information if it's going to have a high boiling point, low boiling point, or if it's going to be a solid, a liquid, or a gas. Now, once we start getting into the organic chemistry of it, and we really start learning more about structures and functional groups and all this other cool stuff, then this is really going to become useful, and you're really going to start understanding how this all ties together. Let's first talk about a London dispersion force. It's the weakest of all the forces. It is between non-polar molecules. Okay, does it even say anywhere on this slide? It says nowhere on this slide. This is between non-polar molecules. Okay, so if you have two non-polar molecules, you have a very, very weak interaction. Okay, is there kind of a, yeah, we'll talk about it there. Okay, it's called a momentary change in electron density. It's what's called a temporary dipole. Okay, weak interaction between the dipoles. All covalent compounds do have this at some extent. Okay, the larger the molecule, the larger the attractive force, the stronger the force is because of surface area. The more surface area, the more of these London dispersion forces you have. Okay, so imagine you have a bromine attached to a bromine. Okay, this is a nonpolar bond, a nonpolar molecule. Nonpolar. All right, I don't have any positive or a negative end to it. Okay, but what happens? Kind of think of like a bucket of water. Imagine you have a bucket of water and you kind of move that bucket. What happens? Well, the water kind of swishes back and forth and back and forth. Okay, well, that's what's happening to the electron cloud. This circle that I drew right here is the electron cloud that's around the bromine, and what's happening is that it's waving back and forth, back and forth, and back and forth. It's not stagnant. So at one moment in time, you have more electrons around this bromine. That's kind of a little. Okay, so it just kind of sloshes this direction. You have more of a partial negative on this side with a little bit of a partial positive on that side because you have less electrons around this bromine, so the nucleus, the positively charged nucleus, is more exposed. Then at the next moment in time, this sloshes back the other direction, and you have the opposite. You have more of a partial negative on this side and a partial positive on that side. And this just keeps doing it, keeps changing back and forth, back and forth. And what happens is at any moment, this negative bromine is kind of attracted towards that positive bromine, and this negative bromine is attracted to this positive bromine. But it's not a permanent, it's a temporary dipole because these electrons might shift the other direction, and now you have like charges and they're no longer attracted towards each other. Okay, and this kind of goes back and forth, and that's kind of what this little picture is trying to show. Okay, they're using this, it's a CH4, which is called methane. This is the structure of methane. All right, nonpolar bonds, you have this electron cloud around it. At one moment, it swashes to the left, and you get more negative on this side, okay, and more positive on that side. All right, and then it causes the other molecule next to it to kind of have more of a negative on this side, all right, and more of a positive on this side. So this side is attracted towards the other side. So more electron density in one region creates a partial negative. Less electron density in one region creates a partial positive. Okay, and these are kind of sloshing back and forth, back and forth. So you imagine this is a very, very weak bond because at one moment it's there, at the next moment it's gone. Now, the larger the molecule, imagine I have, I don't know, 20 carbons and hydrogens and all these carbons. Okay, well, each of these carbons have an intermolecular force. So imagine I have another molecule. So I'll have a force here, a force here, a force here, force, all these forces on one molecule. With our methane, we only just have one interaction. But if you have something that has 20 carbons, we have 20 interactions. So the larger the surface area, the more of these forces you have, the higher the melting points, the higher the boiling points. Like methane has a boiling point negative in the hundreds, something very, very low. It's a gas at room temperature. But a hydrocarbon that has 20 carbons is probably a solid at room temperature. And it's not because it's polar, but it's because it has more of these interactions. Okay? The next intermolecular force is dipole-dipole. This is now between two polar molecules. Okay, so this is formaldehyde. We have a partial positive negative end on our molecules at all times. It's what's called a permanent dipole. Last case, it's switching. This is always there. So this negative end is attracted to the positive end. This negative is attracted to the positive. This negative is attracted to a carbon on another one, attracted to a positive, and so forth and so on. And you have this network. And oh, man. All right, sorry about that. So we have, so this oxygen would be attracted to another carbon, which this oxygen would be attracted to another carbon, and you always have these bonds, all right? And these bonds are very, very strong. They will not break, okay? So that's with a dipole-dipole, okay? The last one is called hydrogen bonding, and this is a special type of dipole-dipole. It's really a dipole-dipole, but it's a special type. All right, and it's the strongest and probably one of the most important when we're talking about living organisms. Okay, and it happens between oxygen, nitrogen, and fluorine. Okay, and with a hydrogen that's attached to. Okay, so let me start over. The hydrogen bond occurs with a hydrogen that's bonded to an oxygen, nitrogen, fluorine, and it's attracted to another oxygen, nitrogen, fluorine lone pair of another molecule. Okay, so you have to have a hydrogen that's attached to either an oxygen or attached to a nitrogen or attached to a fluorine. Remember, these have lone pairs on them. Okay, and these hydrogens are attracted to either an oxygen or attracted to another nitrogen or attracted to another fluorine. Okay, so water, for an example, all right, these, because oxygen has a partial negative, hydrogen has a partial positive, this partial negative is attracted towards a hydrogen on another molecule because it has a partial positive. Okay, and you can see that one water molecule can have several different hydrogen bonds. Okay, this one water molecule can make 4 hydrogen bonds, and they are the strongest of all 3, and they are far the most important. Okay, now hydrocarbons. Let me go back to a hydrocarbon. A hydrocarbon is basically anything that has hydrogen and carbon. This does not have hydrogen bonding. All right, yes, it has a hydrogen, but notice the hydrogen is not bonded to an oxygen, nitrogen, or fluorine. It's bonded to a carbon, so this is a non-polar bond. So because it's non-polar, this is a van der Waals force or a London dispersion force. Okay, so just make sure you're aware, just because there's a hydrogen doesn't mean it's hydrogen bonding. The hydrogen has to be specifically attached to an oxygen, nitrogen, and fluorine. Sulfur also will do it, but we don't see those that often. So why is hydrogen bonding important? Well, our DNA is basically hydrogen bound. All right, our DNA is in a double helix. All right, well, how does it form a double helix? How does it form this really cool network of these two chains? Well, it's completely hydrogen bonding. So these are our base pairs, which we will learn about if you haven't learned about it yet. And you basically, one of the hydrogens is hydrogen bound to an oxygen on another molecule. All right, and you can kind of see these hydrogen bonds. This is a DNA. Okay, so here's a chromosome. Chromosomes are made of DNA, and it's a double helix. It's these two strands. Okay, if you break it down, basically what you have is you have one of these groups. I'll try to get it. One of these groups, which is this group right here. Okay, and you see this is hydrogen bound to one of these groups, which looks like it's trying to be either this or that right there. It doesn't really matter. But basically, this is one of the strands of the DNA. This is the other strand of the DNA, and you have these molecules that are hydrogen bound onto each other, which kind of hold it all together. And you just kind of have this network of hydrogen bonding. Without hydrogen bonding, we would be puddles of slime on the floor. Okay? We are just a network of hydrogen bonding. Also considering how much water we have in our bodies, water hydrogen bonds with all of this. All of our amino acids hydrogen bond. Everything is hydrogen bound inside of our body. This is one of the most important force within our body. Okay, if you ask people like, what's the most important force? Some people might say, oh, covalent bond. Hydrogen bond is the most important force in our environment. Without it, there would be no living organisms. Okay, so this is kind of a summary. London dispersion are weak forces. All molecules have it. Okay, why do all molecules have it? Let's just go back to, we don't really have an example. Well, here, on our formaldehyde. So here I have a dipole-dipole interaction, but notice this hydrogen, carbon, and hydrogen also can have a van der Waals force, or a dispersion force. Because even though I have a nonpolar bond, it still has electrons that are shifting back and forth. So this has both a van der Waals a London dispersion or a dipole-dipole. Okay, but the dipole-dipole is much stronger, so that's the one that we talk about. Okay, so all molecules have it, and they actually show you the formaldehyde. You'll learn how to write structures in a second. Dipole-dipole, moderate bonding. This is something that has a net dipole, and then you have hydrogen bonding, which is between an OH, NH, and an HF. Okay, I kind of like how they show water here, because that technically is a dipole, but it's a special type of dipole. It's hydrogen bonding. Okay, so how is this important for boiling points and melting points? Well, the stronger the intermolecular force, the higher the boiling point and melting point. It's pretty simple. So the boiling point is the temperature at which a liquid is converted to a gas. So basically what you're trying to do is you're trying to break these forces. So let's take water for an example. Okay, we have this force here. When we want to boil this, we have to put in enough heat to start breaking these bonds right here. Because what boiling is each of these molecules are independent of each other. They're no longer bound to each other. So the stronger this bond, obviously, the more energy. The stronger the bond, the more energy is needed. The stronger the intermolecular force, the higher the boiling points. That's why water boils at 100 degrees Celsius. This is a pretty small molecule, but it boils at a high temperature. Okay, so London dispersion forces, all right, very weak forces have very low boiling points and melting points, like in the negatives. Dipole-dipole, higher than the London dispersion, and hydrogen bondings have the absolute highest. Okay, so the boiling point is the temperature at which a liquid is converted to a gas. The melting point is from solid to a liquid. The stronger the forces, the higher the boiling points. All right, increasing strength in intermolecular force, increasing boiling points and melting points. Okay, and here they give you some really cool examples. Here's methane. All right, the mass, I'm going to give you the mass of methane, 12, 13, 14, 15. This is 16 grams per mole, and water is 18 grams per mole. So they're about the same mass, not much of a difference. But look at the boiling points, a difference of 262 degrees Celsius. Methane boils at negative 162, water boils at 100. All right, its melting point is 183 Celsius. Its melting point here is 0 degrees, difference of 183. Okay, so this just shows you how incredibly strong hydrogen bonding is. You have the same mass molecules, but the forces are so different. I'm sorry, the boiling points are so different. So what's going on here? If it's not based on the mass of it, it's based on these forces. This is hydrogen bonding, very strong. This has London dispersion forces, very weak. All right. Here are two nonpolar molecules. They both have London dispersion forces. Okay. This has an extra carbon, so it weighs more, right? Well, it's not just based on the weight. It's based on the surface area. All right. This has 4 carbons. This only has 3. This has a larger surface area. Larger surface. So because of that, because of the larger molecule, it has more forces. It says stronger, but really I like the word it has more dispersion forces. Therefore, it has a much higher boiling point, difference of like minus 42 degrees there. Okay, so more surface area, higher boiling point because it has more intermolecular forces. All right, that is it. Hopefully that review was good. Hopefully you kind of knew some of that stuff and it was a review. If you don't understand anything, rewatch the video, go on YouTube, find other videos on these topics, read it in your book, or read it in your previous Chem 101 book, or come to me in office hours and we can talk more about it. All right, you are now free to start chapter 11.